to name a few. Professor Kim will be giving us a talk which is entitled as Chemically Modified Graphene for Energy and Environment. The stage is yours, sir.
Okay, may I try now?
Yes, sir, please.
Okay, thanks, Chairman. Thanks for the kind introduction. And I would like to thank all the organizers for this nice opportunity. And personally, I would like to also thank to Professor Uday Maiti. Actually, he worked in my group for some more than few years, and he really contributed a lot before joining IIT Guwahati. And just before his talk, I could see that based on his research effort and smart guidance, group is growing now. So I hope good luck in the future of his research group. Okay, then let me start my presentation. Actually, the original title was about energy and catalytic application, energy and environment, but I slightly modified it because I would like to share some general aspect rather than specific application field. So final title is Chemically Modified Graphene for Real-World Application. Okay, this first slide compares ideal material and real-world application. This is an example of silicon material. You know, when you make a silicon device, such as the memory device or any others, firstly, you make highly crystalline, right? Defect-free single crystalline silicon vapor, right? Based on Czochralski method and slicing. Then you will have this kind of a highly crystalline, right? Ideal silicon material. But obtaining this kind of ideal material is just starting point for the eventual real-world application. When you make some real semiconductor devices, you have to do patterning, right, of the kind of circuit, right? We usually use photolithography to this end, and actually this step corresponds to the shape engineering of silicon material. And after that, we also do chemical treatment like doping or any other chemical process for the very delicate, right, optimization and modification of local electrical properties. So I would say for any kind of material application, the making of ideal high purity, high quality material is the first step. But after that, you have to do shape engineering and property optimization for the eventual real world application. That is my some prospect for the general material application. This next slide shows some technical challenges for the graphene material for electronics and optoelectronics. Actually, in the early days of graphene research, large area high quality graphene synthesis was really breathtaking, right? And it's still many scientists over worldwide are still trying to make high quality large area graphene, and target application was much more electronics and optoelectronics. But actually, this very fascinating future prospect has been quite delayed. In the early days, people will try to open the band gap of graphene material. As you know, graphene materials are semi-metallic, right? Materials. So for the eventual electronics and optoelectronics, you like to have semiconductors rather than simple metal. So that's one of the early day challenge, band gap opening, which is still quite challenging now. But nowadays, more critical issue is the preparation of high quality large area graphene itself. It's well known that on the surface of copper or nickel metal substrate, you can apply CVD method to make a high quality graphene. This protocol is really well established, so you can be quite reproducible. But after this synthesis step, you need to separate the single layer graphene layer from the bottom substrate. But the adhesion between graphene and bottom substrate, metal substrate, is rather strong. So high throughput, right? Substrate transfer is quite challenging. So graphene is quite usually damaged or contaminated during this process. So in the case of graphene having a charge carrier mobility dominant electrical property, this kind of defect formation or contamination can easily damage the charge mobility. So as a result, electrical property can be really simply damaged during the post synthetic process. So that's why idealized, right? Electrical properties of graphene is very hard to obtain in the practical real world. So probably in the future, someone can address this issue, but currently industry is suffering from this challenge now. So in the current stage, the commercialization of graphene is much more focusing on powder type graphene rather than large area graphene CW synthesis. But there are quite many number of graphene producers over worldwide, right? But about 5 years ago, there was one article published in Nature entitled "The War on Fake Graphene." Actually, several scientists tried to analyze most of the well-known commercially available graphene powders, right? And actually, based on their careful examination, they could find that most of commercially available graphene powders have more than very high stacking number, much higher than value of 10. Actually, 10 is the kind of standard ISO standard to define graphene material. ISO defined that at least when, if you want to call certain material as a multi-layer graphene, then stacking number has to be less than 10 in average. But in their careful examination, they could not find any commercial sample meeting this requirement. And actually, the reason is the most popular graphene production method is simple physical process by applying very strong shear field. But this simple physical method can temporarily exfoliate graphene, but without any chemical modification, they want to go back to the initial original stacked structure. That's the problem, right? Restacking of temporary exfoliated graphene is the fundamental and unavoidable issue for the physically obtained exfoliated graphene. So that's the problem. That's why it's really hard to find some powder sample which can be really defined as a graphene nowadays. Actually, my research group has been working on nanoscale assembly and chemical modification of graphene for real-world application. Actually, my research group has been working on polymers and many other nanomaterials based on this idea of nanoscale assembly and chemical modification. As I mentioned in the first slide, when you make any kind of a material application, right, you need to do shape engineering and property optimization, right? For the shape engineering, nanoscale or low-dimensional material like graphene, assembly is the root, right? So, for the property optimization, chemical modification is the method. Like as you can recall the case of hetero element doping of silicon, right? Actually, there are two review articles based on this idea. The left one shows directed nanoscale assembly of graphite carbon materials, graphene, carbon nanotubes, and fluorine. And right side one is about chemical modification of graphene. Actually, I would like to emphasize that the right one is read by Dr. Mighty when he was a research professor in my group. And actually, these review articles are highly cited, and I really, I'm still very proud of this comprehensive review article to show our direction. Okay, so I just mentioned that nanoscale assembly can be interesting route for the shape engineering of a nanoscale material. Actually, a nanoscale assembly is indeed a widespread principle in natural living system. You can see the case of virus like COVID-19. Actually, viruses are made from many protein molecules to make a shell structure, and you also incorporate the genetic molecule like RNA or DNA inside. Actually, if you have those molecules dissolved in water, then they spontaneously undergo this kind of shaping and encapsulation to make virus structure. So this is a spontaneous molecular self-assembly, right? Really observed in a natural system. In fact, all living system like our human body itself is based on this kind of molecular assembly to have functions for the including metabolism and any others. Actually, this is a very interesting process, right? Molecule itself has some kind of a power to have this kind of assembly, and in the face of molecule, there is no specific function, but after assembly, you have very interesting function like virus, right? In the case of COVID, it can even threaten entire human race, right? And another interesting point is this is a parallel scalable process. So if you have many molecules, then you will make virus, many viruses at the same time. But the weakness is based on this fundamental interaction issue. This kind of molecular assembly is always based on weak interaction like van der Waals force or hydrophobic interaction or hydrogen bonding. So structure formation can be sometimes retarded, and you may have many defects in the finally ordered structure. So we would like to learn from nature to have this kind of nanoscale assembly to develop as a kind of a tool for the nanofabrication. But in our mass production, right, society, we would like to have high throughput process with low defects. So that's kind of a directed nanoscale assembly rather than self-assembly, right? How to direct nanoscale assembly into desired form and how to promote it and how to improve it. This principle can be applied to graphene-based material like graphene, carbon nanotubes, and graphene. Actually, those materials has very interesting properties and high value, but if you can really tune their material assembly, then you can really boost up the material value and eventual application, right? Actually, in Korea, there is an old wisdom saying that even when you have many precious stones, the real treasure will be obtained when those stones are strung together. I would say this is a kind of old wisdom to justify our idea of a nanoscale assembly, right? Even though individual carbon nanotube, strands, and graphene layer can be interesting, but if you can really control their assembly, they can be even more interesting, right? Actually, my research group is one of the first research group focusing on this issue of a nanoscale assembly of graphene-based material. And this slide shows our early day work. It's been already like 15 years ago. It's about how to induce solution assembly of graphene-based structure into macroporous 3D assembly. Actually, as far as I know, this is the first example of a three-dimensional structure assembly from a two-dimensional material like graphene. Actually, we have been working on graphene as a representative 2D material nowadays, but still we have many other 2D materials emerging nowadays. Semiconducting TMDs and dielectric hexagonal boron nitride, and phosphorin can be also interesting semiconductor, and MXene can be an interesting conductor, right? All those have different compositional feature and different structure, but they have common feature of a 2D structure having very minimal atomic layer structure in
Professor, this is Dr. Maiti. So your microphone, I guess, is muted. We cannot hear you.
Can you hear me now?
Just 20 seconds.
Sir, you are audible. No issue with
Can you hear me now?
Yes, sir.
Can you hear me? Can you see
Yeah,
my slide?
You are
Yes, sir.
audible, sir. You are
Yes,
audible.
sir. You're audible, sir.
Is it fine now?
Yeah, sir. Yeah, sir. Please continue, sir.
Okay. So based on this many kind of a diversity in the 2D material properties and structures, we expect that low-dimensional material assembly can be even more interesting in the future. Actually, recently we published one review article to summarize our idea of 2D material assembly. You know, for the assembly, many 2D materials are obtained in the solution dispersion form in the beginning, and then we apply assembly principle. But in 2D dispersion state, most of 2D materials are suffering from large polydispersity in their 2D shape and size, and they are 2D materials are generally larger than usual molecular level building blocks, and they also have quite strong tendency for restacking. So those are the challenges for the 2D material assembly, but you can apply several different principles to overcome this challenge. For example, I will introduce liquid crystal based assembly to make 1D fibers or any other structure. And surface tension modification can be interesting way to have a large area film in a very fast high yield process. And electrochemical assembly, actually this method route is developed by Dr. Mighty when he was in my group, and can be another interesting route for the 3D assembly. I will introduce those approaches in today's talk. Firstly, I will talk about liquid crystal assembly. As you know, liquid crystal is a kind of a mesophase having crystal-like ordering as well as liquid-like fluidity, right? So in traditional sense, we have gas, liquid, solid, but liquid crystal has some feature of molecular ordering from solid and liquid-like fluidity at the same time. So this interesting intermediate structure can be useful for several interesting applications, such as liquid crystal device, liquid display device, or high mechanical property fiber formation. You know, left side shows optical switching behavior of liquid crystal display. You know, liquid crystalline molecules are combined in the 2D transparent display structure. And by applying some electric field, you can modify the molecular level orientation. Then you can switch on and off for the backlight lighting to pass through this liquid crystal layer. This is a very simple, interesting switching method widely used in liquid crystalline display. And right side shows high, extremely strong liquid crystalline fiber formation like aramid fiber. In this case, you usually use high molecular weight polymer liquid crystal. Actually, usual polymers can be also fiber spinned, but molecular orientation is rather low because of the intrinsic entropic elastic behavior of a single polymer molecule. But in liquid crystalline state, you can get highly ordered molecular orientation in the final polymer fiber state. So this kind of a easy controllability of molecular ordering is a kind of a general feature for the liquid crystalline material. Then how about 2D liquid crystal like graphene, 2D graphene-like structure for the liquid crystal? Left side shows schematics for the disc-like liquid crystalline phases like discotic nematic or discotic smectic or columnar structure. You know, in all those different liquid crystalline structure, 2D discs are oriented in the same direction, right? So if you use these liquid crystalline state as a precursor for the some processing, then you will get highly stacked 2D structure in a very easy way. So those are right side shows graphene fibers and nexium film having highly stacked structure. Without liquid crystallinity, those 2D layers are rather randomly oriented. Then even though each layer can be interesting, but random stacking can yield a very poor property. But by using this liquid crystalline processing, you can get this kind of highly stacked state for the optimal macroscopic properties based on 2D structure. That's why we are interested in liquid crystalline state of 2D materials. For 2D liquid crystalline assembly, graphene can be chemically modified. In original, graphene has many interesting properties, but it has very poor processability and low dispersibility in common solvent. But after oxidation, you have graphene oxide, as shown in the right side. And actually, this graphene oxide can be mass-produced, and it also has a high solution processability. And other than that, those oxidized functional groups can be further exploited for the nitrogen doping or any other chemical modification. Actually, graphene oxide research was initially introduced by Professor Rodney Ruohoek, but if you just simply follow a well-known Hummer's method, then you will see solid precipitation of graphene oxide for such a low concentration dispersion. But we found that is due to the impurity effect, right? After our careful verification, we could see that we see some precipitation again, but this precipitation is not a solid precipitation anymore, but it's an interesting liquid crystalline state. Actually, in general, in basic colloid science, actually impurity effect is well known based on DLVO theory, right? If you have many ionic impurities in electrostatic dispersed particle, then dispersion among the neighboring colloids can be weakened by the ionic impurities, right? Because ionic impurities can have some screening effect. So that's why you need to remove ionic impurity when you want to have high dispersibility from a electrostatic based colloid like graphene oxide. Graphene oxide has many oxygen functional groups, so deprotonated oxygen functional groups have net negative charge. So it's a well-known negatively charged colloidal particle. And those ionic impurities, including some metallic impurities, can also be critical for the further application. Sometimes you have very toxic, right? Impurity like acid, then any material without based on graphene oxide without purification can be toxic, and it can be also corrosive, right? If you have metallic impurity, then there will be some undesirable, right, electrochemical reaction, which can be critical for catalyst or energy application. And those ionic impurities can also yield to the poorly controllable surface energy, and you also have a unstable electrical and thermal properties due to the impurities also. So anyway, you must remove those ionic impurities for the good dispersibility as well as stable property in the final graphene-based structure. Actually, my research group was very fortunate to discover graphene-based liquid crystal for the first time. After our careful effort for the high purity graphene oxide synthesis, we could see that there is a spontaneous formation of graphene oxide liquid crystal in water dispersion, right? And actually, all the graphene oxide platelets are monolayer exfoliated, so that's the resultant high aspect ratio in the discotic structure yield this interesting nematic type liquid crystal. You can directly visualize liquid crystalline ordering by SEM observation after freeze drying of water. You see all the graphene platelets are cooperatively aligned, and you can also identify some typical discrimination structures for nematic liquid crystals, such as half discrimination or integer discrimination. So this is the direct evidence showing that graphene oxide liquid crystal is the typical discotic nematic type liquid crystal. And after our careful verification, we could get almost 100% monolayer exfoliated graphene oxide. That's why, right? We can get very high, very interesting liquid crystalline property even for relatively low concentration dispersion in water. And all these monolayer exfoliated graphene oxide can be carefully reduced to have a high quality minimal number stacked graphene powder material, as I will introduce later. Actually, for this liquid crystalline state in water dispersion, you can also incorporate water-soluble polymer to have a three-component liquid crystalline system. And based on this polymer-based gel structure, you can try to get some fiber structure by wet spinning. And after drying, you see, based on the liquid crystalline property, all the graphene platelets are highly oriented in the 5-axis direction. Actually, we are very proud that our discovery of graphene oxide liquid crystal really initiated academic research interest for the 2D based liquid crystal structure. In fact, before our discovery, there was one well-known 2D based liquid crystal, which is clay liquid crystal. You know, clay is a ceramic layered structure, right? So if you prepare it in a high purity structure, then you will get well exfoliated platelets in water. And that clay exfoliated state is also known to form liquid crystalline state for a while, but without any specific interesting application, there was no big research attention to this state. But right after our discovery of graphene-based liquid crystal, many other research group reports that other way of graphene dispersion can be also lead to liquid crystalline state, and even dispersions of some other 2D material like molybdenum disulfide TMDs or MAXIN also show liquid crystallinity, and they also lead to many interesting applications based on high ordered structure of 2D based liquid crystal. So we are very proud to see that our discovery of graphene oxide liquid crystal really initiated the research field area of 2D based liquid crystal. And graphene based liquid crystal is also interesting in many different material fabrication. Based on liquid crystalline dispersion state, you can simply spin all graphene fiber structure. So this is very low cost counterpart for the traditional carbon fiber, right? And sometimes you can get highly